Hi guys, welcome to my YouTube channel Physics Prince. My name is Deepak. I'm going to teach you all 9 subjects of physical science in detail. My courses are absolutely free of charges. My courses are going to help the students who are preparing for CSIR, NET, GATE, NT exam, PhD exam, SET exam, Jest, TIFR, IIT-Jam exam, and other exams related to physical science. My courses are absolutely uh, free of charges. So, guys, I would request the people who haven't subscribed my channel yet, please subscribe my channel and watch my lectures, which are going to help you to crack the exams related to physical science. Okay, so this is the lecture number 13 of mathematical physics. We are discussing matrix. So this is the fourth part of the matrix, which I'm going to discuss today. Okay, so now I'm going to start, guys. Okay, okay. So this is the lecture number 13 of mathematical physics, in which we are studying matrix. Okay, and this is the fourth part of the matrix. Okay, so here we are going to study Hermitian matrix. Okay, Hermitian Hermitian matrix. Okay, Hermitian matrix. So Hermitian matrix means, right, this is a dagger. We know that is a dagger equal to, if a dagger equal to a, okay, and that is called Hermitian matrix. Okay, if this is the case, then this matrix A is called Hermitian matrix, and a dagger is that is transport of conjugate of A, or we can write uh, conjugate of transpose of A. Okay, conjugate of transpose of A. Okay, so this is the meaning of a dagger. Okay, and there is some properties of the Hermitian matrix, that is principal PD, that is principal diagonal element. Okay, principal diagonal elements are real for Hermitian matrix. Okay, principal diagonal matrix, principal diagonal elements principal diagonal elements are real. Okay, so for a Hermitian matrix, always the principal diagonal elements will always be real. Okay, okay. So principal diagonal element, we also say PDE. PDE, that denotes principal diagonal elements. Okay. Well, now for Hermitian matrix, uh, number of independent term, number of independent term, independent number of independent term, number of independent terms for Hermitian matrix equal to n square, right? If n cross for n cross n matrix. Okay, n cross n matrix. Okay, if the matrix is n independent components or number of independent terms are term equal to n square. Okay, if 3 cross 3 matrix is there, then the number of independent terms is 3 square, that is 9. Okay, similarly for 4 cross 4 it is 16. Okay, very important, number of independent terms, n square. So I'll give you example. Okay, is 2 plus this matrix 2 plus 2 3 plus I, okay, 2 3 plus I, 3 minus I, and 4. We need to check whether this matrix is Hermitian or not. Okay, so matrix A is given 2 3 plus I, 3 minus I, 4. Okay, we have to check whether this is a Hermitian matrix or not. For Hermitian, for this matrix to be Hermitian, A dagger should be equal to A, right? This is for the condition for Hermitian, right? So what we are going to do is, and we know A dagger is A conjugate, transpose of conjugate of A. Okay, this, or we can say uh, conjugate of transpose of A. Okay, okay, so now we'll find out first conjugate of A. Okay, conjugate of A is going to be 2, and this is iota, right? So this is going to be just checking whether my internet is working fine or not. Okay, so now this is conjugate is going to be 2 into 3 minus iota. We'll replace iota by minus iota for getting conjugate of matrix. Okay, so 3 minus iota is going to be plus iota 4. Okay, this is conjugate of it. Now we will find transpose of conjugate of it. Okay, transpose of conjugate of it. That is, so this is the conjugate of A, right? So we'll change rows into columns into row, and we'll get transpose of the matrix. Okay, transpose of conjugate of the matrix. So this is going to be 2 3 plus iota, this column changes into row, and then 3 minus iota 4. Okay, 2 3 plus iota and 3 minus iota 4. So this is, and this is A dagger, right? So we can see from here, we can see that A dagger is A, because we have got this A, the A dagger. This is this is A dagger, and A is also the same. A and A daggers are same too. It means this matrix is Hermitian matrix. This implies A. We have verified this matrix. Okay, so A is Hermitian matrix. Okay, let me just check, am I audible or not? Matrix. Okay, anti-Hermitian matrix. Okay, so anti-Hermitian matrix means A dagger equal to minus A. Okay, or we can write A dagger, that is A transpose of conjugate of A equal to minus A. Okay, so if this is the case, then the matrix A is called Hermitian matrix. Okay, Hermitian matrix. Okay, we'll verify this as well, and there are some properties of Hermitian matrix, that is principal diagonal elements. Okay, PDE, that is principal diagonal elements are either 0 imaginary. Okay, so PD, that is principal diagonal elements, are either 0 or purely imaginary. Okay, and for this anti-Hermitian matrix, independent components, number of independent components, number of independent number of independent component number of independent components equal to number of independent components to n square for n cross n matrix. Okay, n cross n matrix. If it is 3 cross 3, then number of independent terms and 3 square, that is 9. Okay, number of independent components equal to n square. Okay, so we'll verify this as well. So we have been given, right, we have been given example. So we have been given a equal to iota, this is going to be 2 minus iota. Okay, and this is going to be minus 2 minus iota. Okay, and this is iota. Okay, now we'll find transpose of conjugate of a, right, that is a dagger, which is equal to transpose of conjugate of a. Transpose of conjugate of a, and that is going to be we'll change this column into row and this row into column, right? We exchange the columns and row. So this is going to be minus iota minus 2 minus iota. Okay, and this is going to be 2 minus iota and iota. Okay, so this column become the row and this column become the second row. Okay, we have exchanged the rows and columns. Okay, this is the one, and from here we can take minus common. Okay, we'll take minus common, so it is going to be iota minus common, so it is going to be 2 plus iota. Okay, and this is going to be minus 2 plus iota, because we have taken minus common, right? Minus common, so it is minus 2 plus iota, and this is going to be minus iota, and this is equal to minus a. This value is a, right? It's minus a, this one. So we can see a dagger. We can see a dagger equal to minus a. That means a dagger equal to minus a. This means this matrix implies matrix A is anti-Hermitian. Anti-Hermitian. Okay. Okay, so A is anti-Hermitian. So we have verified this matrix. Yeah, this matrix is anti-Hermitian. Right, guys? I hope you understood it. Okay. So next we are going to study. So this is also very important. Next point. Next point is if A is Hermitian, if A and B are Hermitian matrices, Hermitian matrices. Okay, we can say this one. A is Hermitian matrix. Okay, A is Hermitian means A is Hermitian. This implies A dagger equal to A. This is the definition of Hermitian matrix, right? And we need to find out B, IA. Okay, B equal to IA we need to find out. Okay, so this is going to be iota and matrix A, right? Or it means then uh, we'll find now B dagger. Okay, so B is this iota A, and we have to find B dagger. B dagger is going to be minus iota A minus iota A dagger, right? Sorry, my apology. This is iota A dagger, right? And we'll open the dagger. So the dagger of iota is going to be conjugate of transpose of iota, that is minus iota, right? And minus iota into A dagger, and A dagger equal to A, so this is going to be minus iota A, right? So this is, so B dagger equal to minus iota A, or we can see iota A is B, right? So this is minus B. So we can this implies B is anti-Hermitian, okay? Anti-Hermitian, okay? So B is anti-Hermitian, and or where B is iota A, okay? So this says if A is a Hermitian matrix, right? IA is going to be, if you multiply that matrix with iota, then this matrix is going to be anti-Hermitian, okay? Next point. Next is a very important point. Okay, this is minimum number of real elements. The minimum number. Okay? Minimum number of real elements. Minimum number of real elements in n cross n Hermitian matrix. N cross n Hermitian matrix. Matrix is, that is n. Okay. So minimum number of real elements in n cross n Hermitian matrix is n. Okay. That is PDE, principal diagonal element. Okay. Similarly, the minimum number of real elements, minimum number of real elements, minimum number of real elements in n cross n anti-Hermitian matrix is 0. Okay, so number of real elements in n cross n anti-Hermitian matrix is 0, and the of Hermitian matrices are real. And here we can see the principal diagonal elements of anti-Hermitian matrix are either 0 orthogonal matrix. Okay, what is orthogonal? Determinant of A will be equal to plus minus 1. Okay, so determinant should be either 1 or minus 1, and A transpose of A will be equal to A inverse, or if you multiply the matrix with its, okay, so that is determinant of the orthogonal matrix should be of unit modulus, or we can say we can also say this in language, determinant of A should be of unit modulus. Okay, unit modulus, unit modulus. So determinant of A should be unit modulus, means determinant of A will be either 1 or minus 1. Okay, so should be of unit modulus. Okay, next point. These are very important properties I'm going to write, and then I will solve one question which is asked in 2000 CSIR NET 2017. Okay, based on the properties of orthogonal matrix, which I'm going to write for you. Okay, next is very important property. Each row and each column, each row and each column is row. Okay, so psi star psi going to be 1. Okay, each row and each column is normalized vector. Okay, so psi where psi is one row. Okay, one row or column, either row or column. Okay, so psi star psi is going to be 1. That is called normalized vector. Okay, next, any two rows orthogonal to each other. Okay, very important. Any two rows, okay, any two rows or columns will be orthogonal to each other. Okay, this is also very good, very important property. Now I will explain these two property by example. Okay, okay. Next example is, suppose we have this A vector is orthogonal vector. Okay, cos theta sin theta minus sin theta cos theta. Okay, this is an orthogonal vector, guys. How? If we check its determinant of it, if we are going to check, so this is going to be cos square theta minus minus plus sin square theta, and we know this value is 1, because for there is a condition for being orthogonal matrix, their determinant must be equal to plus either 1 or minus 1, plus minus 1. Okay, so this is 1, so this is orthogonal matrix. Now the first is, each row and each column is normalized vector. Okay, that means, suppose psi equal to each, we are taking this column. Okay, sin theta, sorry, my apologies, I'll write in next page. And so I'll write psi is going to be this. I have taken this column. Okay, sin theta, sorry, cos theta minus sin theta, cos theta minus sin theta. Okay, I have taken this cos theta minus sin theta. So this statement is saying each row, any row, okay, each row and each column is normalized vector, that is psi star psi equal to 1. So this is the row which we have taken. So we'll take its conjugate, this means this one, right? And this is going to be, these are real, this is going to be cos theta minus sin theta in matrix form. Okay, conjugate of this is going to be like this. Okay, so now we'll find this psi star psi. So this is going to be can write psi, okay, in cat form. So this is going to be cos theta minus sin theta. This matrix, row matrix, this will psi star means you convert this into column matrix is going to be row matrix, okay, and this is going to be cos theta minus sin theta, right? This one, and square theta plus sin square theta, right? And this is going to be 1, right? So this is going to be 1, implies psi star psi equal to 1. So this is what this statement is saying. Each row or column is normalized vector, okay? So we can see we have taken one column and we have got then psi star, and we have checked it and we've got psi star equal to 1, means each row or column is normalized vector, okay? This one very important. Now similarly we are going to verify, we are going to explain this one, this point, like this one. Any two rows or columns will be orthogonal to each other. Orthogonal to each other means that is orthogonal to each other means psi star psi is going to be 0, okay? So how? So we have taken any so we have taken this any two rows, okay? We have taken two rows, that is psi 1, we have taken it from here. This is the matrix cos theta sin theta, cos theta sin theta. This is the we have taken, and psi 2 row, one row of the matrix we have taken. Any two rows or two columns, okay, will be orthogonal to each other. I have taken this row and this row. And second is minus sin theta cos theta, okay, minus sin theta cos theta. So now this is going to be psi 1 star is going to be, this will convert into column, okay. This is going to be cos theta sin theta, okay, and psi 2 star is going to be, psi 2 star is going to be, this will get converted into column, minus sin theta cos theta, minus sin theta cos theta, right? Right? If we take this one, psi star, psi 1 star, psi 2, if we take, okay, so this is going to be psi 1 star, this is cos theta sin theta into psi 2, this one minus sin theta cos theta, minus sin theta cos theta, right? Cos theta sin theta, and this is going to be plus, if you multiply it, sin theta cos theta, and this is going to get cancelled, 0, right? So we can say is 0. Similarly, psi 2 star psi 1 is 0, going to be 0, right? So this one very important, any two rows or columns will be orthogonal to each other, okay? So this is the ortho, so it means psi 1 star psi 2 or psi 2 star psi 1 is going to be 0. Very important thing. Now okay, so this is orthogonal, so this is satisfying orthogonal. So 2, that means any two rows or columns are orthogonal, okay, yeah, okay, will be orthogonal to each other, okay. So now I have explained this property. Now I'm going to solve one question for you, okay, which is asked in CSIR net and BC. A0 and BC are orthonormal to each other. Orthonormal, orthonormal, orthonormal to each other. Orthonormal to each other. Okay, then ABC, value of ABC you need to find. Okay, this one. So two vectors A0 and BC are orthonormal. Okay, they are that means they are normalized as well as orthogonal. Orthonormal means normalized plus orthogonal. Okay, to each other. Then we need to find out value of ABC. How we are going to solve it now? Since we have been given psi1 is given A0. Okay, so it means we'll find that implies psi1 star is going to be A comma 0, right? Similarly, psi2 is given BC. This implies psi2 star is going to be BC. This will become this is column matrix and this will become row matrix. Okay, BC, right? Okay, so because we have psi1, so we have find psi2 and psi1 star and psi2 star. So this question is saying, right, these two properties are going to be okay. So this question is saying two vectors, these are orthonormal, right? They are normalized plus orthogonal. So for normalization means they are orthonormal, they are normalized. That implies psi1 star psi is going to be 1. That is the one, right? So psi1, this is psi1, psi1 is given. So we have found psi1. So psi1, if you do product of psi1 star with psi1, it is going to be 1, right? So we'll solve it. So this is going to be A0 into A0, right? We'll solve it. So this is going to be, and this is going to be equal to 1. So this implies A square plus 0 equal to 1. This implies value of A is going to be plus minus 1. Okay, value of A is going to be plus minus 1. Well, so this is the value, right? Because they are orthonormalized, right? So because we know this one, each row and column is normalized vector. Okay, so this is the row, column is given, right? We have found the row and then we made psi star psi1. This will be because they are, each row and each column are normalized, right? So this is the value of A we have found, right? Next we'll find for this psi2 star psi2, because this is psi2 side, because this is also a column vector, right? So each column or row are normalized vector, right? So these are they are normalized, right? Because orthonormal condition is given, are orthonormal, right? So this is going to be psi star is BC, and this is going to be BC, right? We'll solve it. So this is going to be B square, and this is going to be 0, sorry, 1. They are normalized, right? Orthonormal normalized. So this is going to be B square plus C square equal to 1. This is equation number 1. Similarly, now we'll use this property. This one. any two rows or columns will be orthogonal to each other, right? Because they are orthonormal. So orthogonal means psi1 star psi2 is going to be 0. Okay, so psi1 star, this one, a0, that implies a0 into psi2. The value of psi2 is bc, right? So bc, this is going to be bc equal to 0. We'll simplify it. So this implies ab plus 0 equal to 0. This implies ab equal to 0. Since a not equal to 0, because a is plus minus 1, this implies b equal to 0. So value of b we have found. Okay, so from equation 1, value of putting value of b in equation 1, so this is going to be 0 plus c square equal to 1. This implies value of a equal to plus minus 1. Okay, so now value of a equal to plus minus 1, value of b equal to 0, and value of c equal to plus minus 1, right? Very good question, and based on these two properties. Okay, and this is asked in June 2017. Well guys, I hope you understood it. Okay, next. Next is if A and B, AB will also be orthogonal. AB will also be orthogonal, right? This implies A into A transpose equal to I, and A transpose equal to A inverse. This is the condition for orthogonality, right? And B is also orthogonal, right? So B into B transpose is going to be I, and B transpose is going to be B inverse. Okay, B inverse, right? Now we have to find AB. If AB is also orthogonal, it means AB into AB transpose will find out, and that should be I, right? If this value will give I, this means AB is also orthogonal, right? This here AB we are going to check. So this is going to be A, B. So this is going to be AB, right? And we'll open it. This is going to be B dagger, A dagger, right? We know how to open AB dagger, right? This one. And this is going to be A, B, B dagger, A dagger. And since B dagger equal to B inverse, right? This is going to be B, B inverse, A dagger. And this is going to be B, B inverse is I, right? Identity matrix. I, A dagger. This means A, A dagger. A dagger is A inverse, right? So A inverse, right? And this is going to be I. So we have found AB into AB transpose of AB is iota. It means that implies AB is also orthogonal. Orthogonal. Okay. So very important property. If AB are orthogonal, then AB will also be orthogonal. Okay. Next point. Next, unitary matrix. Okay. So what is a unitary matrix? Unitary matrix. Unitary matrix. Okay. Unitary matrix means we have learned that Hermitian and anti-Hermitian, right? Unitary matrix means this is for orthogonal. This is for orthogonal condition, right? Now we are going to study for unitary matrix. Okay, orthogonal. Now unitary. Unitary matrix means A. If A is unitary matrix, it means A dagger. A dagger is going to be equal to A dagger A is going to be equal to I. Okay, and this implies A dagger is going to be A inverse. Similarly, right? Here we did some mistake. This is not dagger, this is the transpose, guys. Okay, transpose, transpose. This is transpose, this is transpose. These are transpose. Okay, and this I. Okay, so for unitary matrix, it's these are transpose. Okay, now let me just check. Yes, correct. So this is for orthogonality. Now unitary matrix is like this. Okay, here also we have done some mistake. A dagger or A dagger A should be I. Then A is called unitary matrix and A dagger should be A inverse. Okay, from there. Okay, very important property. And for unitary matrix, there is another condition, that is determinant of A should be plus minus 1, right? In like similar way this for orthogonal, right? Here I have explained for orthogonal this one, right? Orthogonal means we use transpose, and for unitary we'll use dagger. Okay, so A dagger, so determinant of A is plus minus 1, that is plus minus 1, that is called unity modulus, unity modulus. Okay, unitary modulus. Okay, so this is the condition for any matrix being unitary matrix. Okay, A dagger should be equal to A inverse, or A dagger equal to I, and determinant of A should be equal to either minus 1 or plus 1. Okay, now I'll write some properties for this. Same properties like this. Rows and columns are orthonormal. Okay, rows and columns are orthonormal. Orthonormal. It means rows or columns are orthogonal vector. Okay, okay. So that is rows and columns are orthonormal. Okay. Next property. This is if A and B are unitary matrix, A and B are unitary matrix, this implies AB will also be unitary matrix. Okay, it means A dagger equal to A inverse and B dagger equal to B inverse, right? And then we'll find AB dagger, right? This should be I. Okay, so we'll find this is going to be AB, and we'll right? So this is going to be A, this is B inverse A dagger, right? So this is going to be this is I unity matrix I A dagger, or equal to, this is going to be A dagger, and we know A dagger equal to A inverse A inverse, this is I. So we have found AB dagger equal to iota. This implies AB is also unitary matrix. Okay. Now we'll solve some questions. Okay. So this is, we'll check Hermitian or anti-Hermitian. So whether the matrix is Hermitian or anti-Hermitian. Okay. Okay. Next is so we have been given, okay, question given AB are unitary matrix. Okay, this means A dagger equal to A, sorry, AB are Hermitian matrix. Okay, so A dagger equal to A and B dagger equal to B. We have to check other expressions whether they are Hermitian or anti-Hermitian. Okay, first we have to check this one, IAB. It is Hermitian or anti-Hermitian. Okay, so what we are going to do, IAB dagger will find. Okay, so I dagger of iota is going to be minus iota, and this is going to be B dagger A dagger, right? And B dagger and A dagger equal to minus iota, B dagger equal to B and A. So from we can see that AB dagger equal to minus BA. So this is not Hermitian. Not, we have to check Hermitian or not. It is not Hermitian matrix. Hermitian. If it would be Hermitian, this value should be like iota AB. This should be iota AB, right? But this is not the one. So this means iota AB is not Hermitian. Next example. Next example or next question. There is A plus B. We have to check A plus B is Hermitian or anti-Hermitian. Okay, Hermitian or not Hermitian. So we will check A plus B dagger, and this is going to be A dagger plus B dagger, right? And this means A plus B. So we can see A plus B dagger equal to A plus B. This means A plus B is Hermitian of it. Is Hermitian matrix. Okay. Next we have to check A dagger A whole dagger. Okay, A dagger whole dagger, A dagger A whole dagger. Okay, next is this one. Next we'll check for A plus iota B, whether it is Hermitian or not Hermitian. Okay, we'll find out A plus iota B dagger. If this will come equal to A plus iota B, then it is Hermitian, else not Hermitian. Okay, so this is going to be A dagger minus IB dagger is going to be minus iota b dagger, okay, and a dagger equal to a minus I b dagger is not Hermitian, okay. Understand this difference. This is not anti-Hermitian, this is not Hermitian, okay. So there is a difference, right? Okay. Next question. This is a plus, sorry, my apology. This is commutation of AB upon 2i. We need to check whether it is Hermitian or not Hermitian, okay. So again we'll check it. This is going to be AB this is going to be a comma b upon 2i. We'll check dagger, okay. So this is going to be AB, will open it, so this is going to be AB minus BA dagger upon 2i, dagger is going to be minus 2i, okay. And again we'll open it, so this is going to be b plus b plus a dagger b plus minus a dagger b dagger upon minus 2i, and this is going to be this will like because a dagger equal to a, right? So this is 2i, will take minus common and minus minus will get cancelled, so this is going to be ab minus ba upon 2i, right? I checked whether they are Hermitian or not Hermitian. Very simple questions, okay, for practice of properties, okay. Next is eigenvalues and eigenvectors, okay. Eigenvalues and eigenvectors. Okay, so eigenvalues we are going to study. So here first we'll study characteristic equation, okay. Characteristic equation, okay. Characteristic equation, which is, we know, that is a minus lambda I, determinant of a minus lambda I equal to 0, okay. Determinant of a minus lambda I equal to 0, and there is another equation, that is ax equal to lambda x, okay, where lambda is eigenvalue, x is eigenvector, okay. Eigenvector, okay. Now we'll study properties. This is right, this eigenvector, this eigenvalue, and characteristic equation you already know, that is a minus lambda I equal to 0, where I is unitary matrix, a is the matrix, and lambda is the eigenvalues, okay. Okay, some properties we are going to study here, so which we have also studied, that is trace of any matrix is sum of eigenvalues, right? Sum of eigenvalues, that is, let sum of eigenvalues, okay, that is PDE, principal, uh, that is sum of PDE, principal diagonal elements, okay. Second property is determinant of A is product of eigenvalues, product of eigenvalues, okay. Next is that is eigenvalues of matrix A equal to eigenvalues of transpose of matrix, okay, both are equal, okay. Eigenvalues of A equal to eigenvalues of transpose of A, okay. So this is what it is. Eigenvalue of A equal to eigenvalue of transpose of A. So whatever the eigenvalues of A will be, the same values will be of transpose of that matrix, okay. Next, if lambda 1, lambda 2 and lambda 3 so on are the values of any matrix, in that case the eigenvalues eigenvalues of A inverse will be 1 upon lambda 1, very important guys, 1 upon lambda 2, 1 upon lambda 3, so on, okay. Similarly, eigenvalues of, because A values are this, right, eigenvalues of e to the power A is going to be e to the power lambda 1 comma e to the power lambda 2 comma e to the power lambda 3 and so on, lambda 3 and so on. Similarly, eigenvalues of Ka is going to be K lambda 1, K lambda 2, so on. And eigenvalues of, very simple, eigenvalue of A to the power n is going to be lambda 1 to the power n comma lambda to the power n comma lambda 3 to the power n and so on, okay, right. So these are important properties guys, okay, which will be used in the question. Next, and real eigenvalues, okay, real eigenvalues. So if you want to find real eigenvalues, you will find which matrix, okay. So real eigenvalues you will find if matrix is symmetric matrix, then you will find real eigenvalues, okay. If there is a symmetric matrix, then the eigenvalues of symmetric matrix are real, okay. Similarly, for Hermitian matrix, okay, Hermitian matrix, for Hermitian matrix eigenvalues will be real, okay. Next, uh, zero or purely imaginary eigenvalue, okay, zero or purely imaginary eigenvalue values, okay. So for what matrix you are going to get eigenvalues, either zero or purely imaginary, okay. For antisymmetric matrix, for antisymmetric matrix, or we can say skew-symmetric matrix, okay, eigenvalues will be purely imaginary or uh, either or zero, okay. Second, for anti-Hermitian Hermitian matrix. For anti-Hermitian matrix, okay, eigenvalues will be either 0 or purely imaginary. Okay, anti-symmetric matrix, we can also say skew symmetric matrix to anti-symmetric matrix. Okay, okay, okay. Next, is eigenvalues. Eigenvalues which will be unit modulus, whose eigenvalues will be unit modulus. We have to name those methods. Okay, eigenvalue unit modulus. Unit modulus means the eigenvalue will be either plus or minus. So plus one value will be unit modulus for the matrix. Number one, orthogonal matrix. Orthogonal matrix. If it's orthogonal matrix, then eigenvalues are going to be -1 and +1. Okay, that is called unit modulus. And second is unitary matrix. Unitary matrix. Okay. Next. So eigenvalues are +-1 for this. Okay, unit modulus we can say. Next, eigenvalues, very important properties. Okay, eigenvalues equal to PDE, that is eigenvalue will be equal to principal diagonal elements. Okay, eigenvalue will be principal diagonal element. Okay, PDE. For what matrices the eigenvalue will be equal to principal diagonal elements, and those matrix will be diagonal matrix, diagonal matrix, diagonal matrix. Second is upper triangular matrix. Upper triangular matrix. Number third is lower triangular matrix. Lower triangular matrix. Okay, so eigenvalue will be equal to principal diagonal element for diagonal matrix. If it's diagonal matrix means all the elements will be 0 except diagonal elements, right? And upper triangular matrix, all the elements will be 0 which are below the diagonal elements. Okay, so if you have diagonal element upper triangular matrix or diagonal matrix or lower triangular matrix, then the eigenvalues are going to be equal to the principal diagonal elements. Okay, eigenvalues will be principal diagonal elements. Okay, next point is eigenvalues will be equal to 0 for what matrices the eigenvalues are going to be 0. First is null matrix. If it is null matrix, then eigenvalues are 0. Okay, second, nilpotent matrix. For nilpotent matrix, okay, nilpotent matrix. If it's nilpotent matrix, nilpotent definition of nilpotent matrix is if a to the power p is any integer equal to 0. Okay, in that case we call nilpotent. For nilpotent matrix, it is going to eigenvalues are 0. Next point is eigenvalues 1. Okay, eigenvalues equal to 1 for 1 or 0, 1 or 0, either 1 or 0. For what matrices eigenvalues are going to be either 1 or 0? That is for uh, idempotent matrix, idempotent matrix, idempotent matrix. Okay, and definition of idempotent matrix means square of matrix is going to be itself the matrix. Okay, that is A square equal to A. Okay, so this is about idempotent matrix. Next is eigenvalues. Very important properties, guys. Okay, eigenvalues equal to plus minus 1. So eigenvalues are plus minus 1. Okay, for in involuntary for involuntary matrix, if it is involuntary matrix, then eigenvalues are going to be plus minus 1. Okay, and the definition of involuntary matrix is A square. The square of the matrix is going to be identity matrix. Okay, for this lambda is going to be plus minus 1. Okay, well, this is the one. Next is, okay, so I'm going to stop here, guys. Remaining I'm going to solve in next class, and next class is going to start after 10 minutes of this class. Okay, and guys, I also would request the people who haven't subscribed my channel yet, please subscribe my channel, and thank you so much for watching the video, guys. Bye now.